So in this problem, there's a typo. It says the system is at rest when a constant 30-pound force is applied to the cable. Well, if it's at rest with the 30 pounds, then it's not moving. So what I think it means is that the system is at rest in a position shown, then a constant 30-pound force is applied to the cable. Okay, so let's start with that. And the solution to the problem is going to be energy plus work because of that 30-pound force. So we're going to have T1 plus V1 plus the work done by the force, so from 1 to 2, will equal T2 plus V2. And so remember that T1 is the kinetic energy, 1/2 mv squared. V1 is the potential energy, mgh, and 1/2 kx squared for the gravity and spring, respectively. Okay, so let's just write that all out. I'm going to start down here. 1/2 mv1 squared plus mgh1 plus 1/2 k x1 squared plus the work done from 1 to 2. Let's talk about that later. Will equal the kinetic energy after, potential energy after, both from gravity and the spring. Okay, so let me draw the after picture. So there's that. The bar moves up 1.5 feet, the collar. And so now this cable is going like that. And there's the new dimensions are 2 feet, and that's now 1.5 feet. So we're going to need to know the total length. So let me just do that right now. So 2 squared plus 3 squared square root is square root of 13. And 2 squared plus 1.5 squared is square root of 6.25. So what I'm going to do now is calculate V, H, X, and the work, and then we'll solve. So first of all, to get the H, we need a datum. And so what I'm going to do is I'm going to pick where it was at the bottom as the datum. Okay, so that means that initially H1 is 0. And afterwards, H2 is 1.5 feet. So next, we do the velocity. It says it starts at rest, so the initial velocity is 0. And the final velocity is what we're trying to solve for. Okay, so now we have the X. And remember, it's X from the unstretched position. And so this spring and mass A at start, it's already compressed because, you know, A has some weight and it's sitting on the spring and it's moving down. So the first thing I'm going to do is I'm going to change the K, which is, I'm going to just write 1 2/3 pound per inch, which is 5/3 pounds per inch. Okay, I'm going to change that to pounds per foot because we're doing everything in feet. So 5/3 pounds per inch times 12 inches per foot, that'll equal 20 pounds per inch. 5 times 12 divided by 3 is 5 times 4, which is 20 pounds per inch. Okay, so then initially, before we start, the collar A weighs, 15 pounds. And there's the force of the spring, which is K times X1. And so the energy is 1/2 kx squared, so the force is just kx. In fact, that's how we get the energy, by integrating kx, so 1/2 x squared. Okay, so 15 equals k times x, so we have k times x1 equals 15 pounds. K is 20 pounds per foot. I wrote inch up here. That was the whole point. I was trying to change everything into feet. 20 pounds per foot times x equals 15 pounds. So x1 is 3/4 of a foot. Okay, so x1 is 0.75 feet. x2, we raised it 1.5 feet, so if it was initially compressed 0.75 down, let's see, it comes up 0.75 to 0, and then it stretches another 0.75 feet. Okay, so let me try to draw that. So here it is at 0, and then it gets compressed down to 0.75, and then you lift it up another 1.5 feet, so it's now stretched from the 0. It's just 0.75 because the total lift was 1.5. Okay, so it was starting 0.75 below where it's unstretched. We moved it 1.5 feet up, so it's 0.75 above where it's not stretched. And plus or minus doesn't matter for this because it's 1/2 kx squared. So the last thing we need to do is do the work from 1 to 2. And the work done by that force is the force times how long it moved, or how far it moved. So the force is 30 pounds. And what I want you to see is that if this was originally square root of 13, and then the diagonal, when you move up, turns to square root of 6.25, can you see that this point that was right here, okay, so it was there, it's moved over there a distance of square root of 13 minus square root of 6.25, because the extra length went into the horizontal part of the rope. So the total work is the force, which was 30 pounds, times how far it moved, which is, if it started, the diagonal started at root 13 and it ended at root 6.25, the difference is how much the rope moved. So let me calculate that and come back. Okay, so I get that to come out to be 33.17 foot-pounds. Okay, 30 pounds times that distance. So let's write the whole thing out. So we have 1/2 mv squared is 0, plus mgh is 0, plus 1/2 kx squared, plus the work from 1 to 2, which was 33.17, is going to equal 1/2 mv2 squared plus mgh, so that's the weight times the height was 1.5 feet, and plus 1/2 kx squared. Okay, so I'm going to start putting in some numbers. First of all, that will cancel that. The weight was 15 pounds, and that makes the mass 15 over 32.2. So I'm going to write that out. So we have 33.17 equals 0.2329 v squared plus 22.5. That'll be foot-pounds. Okay, so we'll just solve for V2 and be done. And I get V2 is 6.77 feet per second. Okay, let me go check the solution and come back. And that's right. Okay, so I read these before I turn on